Welcome you all. Myself Manjusha, PCT Physics JNP Wayanad. Today in our physics class, we are going to have a detailed discussion about an interesting topic. So children, do you like music? Yes, I know all of you like music very much, isn't it? And we come across different kinds of sounds in our daily life, just like singing of birds, sounds of various animals, machines, then TV programs, radio programs, etc. etc. So have you ever thought which form of energy is helping us to enjoy all this? Have you ever thought which is helping us to hear all these different sorts of sound? Yes, the form of energy which is helping us to enjoy these different kinds of sound is the energy form called sound. So today we are going to discuss in detail about sound. So in this topic sound, we will be discussing about how the sound is produced, how it is propagating through a medium, what are the characteristic properties of sound wave, then the characteristic properties like pitch, quality, timbre of sound, then also reflection of sound. Okay, then we have to discuss in detail about the multiple reflection and its uses. Then the frequency, wavelength, amplitude, etc. all such characteristics of sound, and again ultrasound, infrasound, then applications of ultrasound, and moreover at last but not the least about the structure and functioning of our ear. Okay, so shall we start? Ready all of you?
So children, do you know what is sound? Yes, as we mentioned earlier, it is the form of energy which produces a sensation of hearing in our ears, right? Produces a sensation of hearing which is helping us to hear anything. Okay. And how is it produced? Or how the sound is produced? Yes, it is due to the vibration of different objects. Sound is produced due to the vibration of different objects. So what do you mean by vibration? It is the to and fro motion of an object, isn't it? To and fro motion of an object is called vibration, and vibration of an object can produce sound. We know there are different kinds of musical instruments. Okay, so like drum, guitar, tabla, flute, etc. In all such musical instruments, you might have observed there is something vibrating. There will be a material, there will be a medium which is vibrating, which is producing sound. We should try to identify the medium or material which is vibrating or which is the reason for the sound produced by the instrument. Okay. So, as we mentioned here in the drum, the membrane of the drum vibrates, producing the sound. And when we play guitar, the string on it makes to and fro motion. That means it vibrates and produces sound. And you might have seen tuning fork, right? Tuning fork, it is having the prongs. The prongs, when it vibrates, produces sound. So we should, my dear children, you should try to identify the material or medium which is producing sound in different kinds of musical instruments or any kind of object surrounding you producing sound. Okay. Now, how sound is reaching us? That means there should be or there will be a source or the speaker, and the sound from that source travels through the medium and reaches the ear. That means the receiver. Medium means it is the matter or the substance through which that sound travels. Okay. And you might have studied it can be any kind of material. That means it can be solid, it can be liquid, or it can be gas. Okay. So the source produces sound and it is passing or traveling through, the sound is traveling through the medium and hence reaches the receiver or the ear. And one particular point you have to keep in mind, it is traveling as a wave. Sound is traveling as a wave through the medium. What is that? Wave. And here sound is a kind of wave called longitudinal wave. Okay. So wave, it is disturbance created in the medium. So this longitudinal wave is having something peculiar in it. So let us see what is that in the coming slides. As I told already, the medium can be a solid, liquid or gas through which the sound can travel. And one particular property of this sound wave is that it travels as successive compressions and rarefactions in the medium. So don't confuse with the terms compressions and rarefactions. Sound travels as successive compressions and rarefactions in the medium. That we'll be discussing in the coming slides. Okay. Now, as you can see in the figure, there is a tuning fork which is vibrating, and this vibrating tuning fork is creating a series of compressions and rarefactions. From the figure, any guess what may be the term C standing for? And what about R? Yes, C is showing the compression. That means the particles are compressed together. Already we discussed now, sound is traveling through the medium and medium contains several particles. So when the vibrating object is, the object is vibrating, the particle also starts vibrating along with it. And as a result, some region there will be more collection of particles in the medium. That means the particles will be more crowded. Such regions are named as compressions. And in some other regions, the particles are very far apart. Okay, as you can see from figure, the regions which are marked as R, there the particles are far apart, not crowded at all. So such regions are named as rarefactions. So such a series of compressions and rarefactions are produced in the medium when sound is propagating through it. Okay, so I hope the terms compressions and rarefactions are clear to you. Compression means the region where the particles are very closer. Okay, more pressure, the area where there is more pressure, or the particles are more thickly packed. And rarefactions means the region where the particles are far away. That means they are not at all closer, it is somewhat far away. Okay, so such regions, such a series of compressions and rarefactions will be created when sound is propagating through the medium. Now, as you can see, as we discussed, the tuning fork, the prongs which is at rest, there will be a continuous or uniform distribution of particles. But when the tuning fork starts vibrating, that means the prong starts vibrating, the particles also starts vibrating, and as a result, you can see when the prong is moving forward, the particles are also pushed forward, and as a result, they become crowded together, creating a region of compression. And the next instant, the prong will be going backward. Okay, so when the prongs suddenly go backwards, then the particles become far apart. Right, they will be creating a region of low pressure called rarefaction. So I hope it is clear to all, right? That means sound, when it is propagating through a medium, it is creating a series of compressions and rarefactions. Okay. Nextly, as I told, the same thing only, compression, and the region of low pressure is called rarefaction. Again, one more figure explaining how compressions and rarefactions are created as the sound is propagating through the medium. Okay, say the case of same tuning fork vibration only. Tuning fork moving forward, prong moving forward, compression, moving backward, rarefaction. By the time it again comes forward, the one rarefaction, one compression, they will be already moving or proceeding, right? So likewise, a series of compressions and rarefactions are created. I hope it is clear to you. Okay. Now, the same thing, that means as you can see from the speaker, the series of compressions and rarefactions are reaching the ears of the receiver or the person who is listening to that. So likewise, the sound is reaching the ears, and There you can note down one more figure showing a wave-like pattern, isn't it? So that wave-like pattern is indicating the same change in the pressure or the density of the particles of the medium. That means we can represent sound as the variations in the pressure or the density of the particles of the medium. That's what the propagation of sound can be visualized as propagation of density variations or pressure variations in the medium. We can see that the compression region is shown as the crest of the wave. Crest, the peak portion of the wave is known as crest. So the compression indicates the crest, or it is indicated by the crest of the wave, and rarefaction is indicated by the trough of the wave. Trough, it is the valley-like portion of the wave. So crest and trough. Crest indicates the compression or high pressure or high density, and the trough indicates rarefaction or the low pressure or low density. Okay, so sound is propagating as a series of compressions and rarefactions which can be visualized as the variations in density or pressure in the medium. Now, next is sound is having another important property. It is called a mechanical wave. Okay, why is it so, or why is it called so? Let us see. Sound cannot travel in vacuum. Do you know what is vacuum? Vacuum means, yes, free space, no particles or no medium. So sound cannot travel in such a free space, right? So it is called a mechanical wave because it needs a material medium like air, water or steel, something like that for its propagation. It cannot travel through vacuum. Always a medium is required because the motion of the particles in the medium characterizes the sound wave. Okay, so hence the sound wave is called a mechanical wave, right? Nextly, the same thing we can explain or we can prove with the help of a bell jar. Okay, bell jar experiment can be used to prove the particular mechanical property of, the mechanical wave nature of sound can be explained by bell jar experiment. So here there will be a bell jar. The bell jar indicates that a closed jar, tightly closed jar which is having an electric bell inserted in it. Okay, as you can see in the figure, this is the bell jar, and there will be the cork using which the jar is tightly closed. Okay, and then we have the electric bell, and the electric connection will be given from outside. Okay, and at the bottom of this bell jar you can see there is a vacuum pump connected. Vacuum pump, it is meant for creating vacuum or sucking air from a region. So this particular bell jar experiment, when initially there will be air inside the jar. Okay, so when you operate the electric bell or when you switch on the electric bell, we will be able to hear the sound of the bell. But once we start the vacuum pump, the amount of air inside the jar starts decreasing, right? So as the amount of air particles in the jar goes on decreasing, the sound, the intensity of sound that we can hear, that also become feeble like that. That means we at last at a particular point when there is no air at all inside the jar, we cannot hear any sound at all, even though the bell is working or bell is functioning, right? Okay, so bell jar experiment is the experiment which can prove the mechanical nature of sound wave. Okay, so it is an important experiment, bell jar experiment, kindly note down. Now, characteristics of sound wave. As we know, the sound can be visualized as variations in density or pressure. Okay, that means density will be varying from maximum value to minimum value, again to maximum value, like that. So one such variation from maximum to minimum, again back to maximum, that is counted as one oscillation, one complete oscillation. And hence the distance between two consecutive compressions or two consecutive rarefactions is called the wavelength. Okay, wavelength. We seen that sound can be visualized as a wave. Okay, so it is having a characteristic property called wavelength. So it is the distance between two consecutive compressions or two consecutive rarefactions, that is called wavelength. It is denoted by the Greek letter lambda. Okay, Greek letter lambda, and its SI unit is meter. As you can see from the figure, this is the wavelength. That means distance between two consecutive crusts have been noted as the wavelength. So crust, you know, it is indicating the compression. So distance between two consecutive compressions or two consecutive rarefactions is called wavelength. Okay, and also in the same figure you might have seen it is marked there as amplitude. What is amplitude? That you might have studied in lower class, right? As you can see, it is the distance which is the particular wave or the crust of the wave is having from its middle or the mean position. Okay, so actually the amplitude is the magnitude of disturbance in a medium on either side of the mean value. That means, as you can see in the figure, it is the distance between mean position and the crust. Mean position and the crust or the compression, that is called amplitude. That means maximum how far the particle of the medium can move due to the vibration. That is called amplitude. It is denoted by the letter A. Nextly, next characteristic property is the time period. As you know, time period is a time taken to complete one wave or one oscillation. Okay, that means one oscillation of the density or pressure of the sound wave. That is called time period, denoted by the symbol capital T, capital letter T. SI unit is second. Then the number of complete oscillations in unit time. How many oscillations are produced or how many waves are produced in unit time, that indicates the frequency of the wave. What is it? Frequency. That will be a new term for you. Frequency of the wave. It is denoted by the Greek letter nu. Nu, the symbol you have to study carefully because you may be getting confused with the V. It is not V, it is nu only. While writing, you should take care of it. Okay. So number of complete oscillations in unit time is called the frequency, right? Or number of repetitions per unit time. And its SI unit is hertz. Hertz or 1 by second. Okay. Frequency SI unit is hertz. Then another property is speed of the wave. You know, sound is having speed, and this speed V is denoted by the letter V. The speed V, frequency nu, and the wavelength lambda. All these parameters you can relate by the equation V is equal to lambda nu. What is it? V is equal to lambda nu. V stands for speed. Speed is equal to wavelength into frequency. If you know the wavelength and frequency of a sound wave, you can calculate the speed of the wave. Okay, very important equation. V is equal to lambda nu. Speed is equal to wavelength into frequency. And SI unit of speed, as you know, it is meter per second itself. Okay, so the same thing, density variations or pressure variations, and the amplitude you can note, it is given or shown in the figure. Then the wavelength lambda. It is the density or pressure variations plotted against the distance. Okay. So the visualization of the density variations or pressure variations as sound wave. Now, you know, sound travels in different media. Okay. So can the sound travel through same speed in all such media. That means sound can travel to solids, liquids and gases. So can the sound travel with the same speed in all the three media? Any idea? Okay? Yes, as you know, sound can travel faster in solids. Okay? Why? As you come from solids to liquids and then to gases, the speed of sound will be decreasing. That means it will be having very low speed in gases and it can travel faster in solids. Okay? And so nature of the medium decides the speed of the sound, and another parameter is temperature of the medium. Temperature also decides the speed of the sound. And do you know why in solids the speed of sound is more? In solids, you know, the particles are very tightly packed. Okay, so once the solid material is set into vibration, that energy, that means that vibration can be passed from one particle to another very fastly because the particles are very closer, right? That's why in solids sound is traveling faster compared to liquids or gases. So speed of sound decreases when we go from solid to gaseous state. Okay. Then coming to the case of temperature, in any medium, as we increase the temperature, the speed of sound also increases. As the temperature of the medium increases, speed of sound also increases. That means the speed of sound in air is 331 meter per second at 0 degrees Celsius, but it is 344 meter per second at 22 degree Celsius. Okay, so as the temperature increases, the speed of sound also increases. So the speed of sound in different media at a particular temperature, there is a table given. That means, as you can see, solid particles, liquids, gases. This is the speed of sound at 25 degrees Celsius, and the speed is mentioned in meter per second. As we know, solids will be having, or sound can travel faster in solids. Okay. So at 25 degrees Celsius, as you can read from the table, aluminum. Yes. It is through aluminum, sound can travel at a speed of 6420 meter per second. Okay. While in water, in sea water, it is 1531 meter per second only. So as we come from solid to liquid, we can see at the particular temperature, the speed of sound decreases. Again, when we come to gases, further the speed of sound decreases. Okay. So you have studied reflection of light. Okay, just like that, sound wave also undergo reflection from a solid or liquid or any particular material on which it is falling. So the sound wave also follows the same laws of reflection. You might be remembering or try to recollect what are the laws of reflection of light. The same thing is applicable in the case of sound also. So as you can see, incident sound wave is incidenting on any reflecting surface. Then after touching on the reflecting surface, the sound wave get reflected back. Okay. And the angle between the incident sound wave and the normal, it is called the angle of incidence. The angle between reflected sound wave and normal is called the angle of reflection. Normal, you know, it is the perpendicular drawn to the point of incidence at the reflecting surface. Okay. So angle I, angle R. So hope you remember the 2 points in the laws of reflection. The angle of incidence is equal to the angle of reflection. Similarly, next one, the incident ray, the reflected ray are normal at the point of incidence, all lie in the same plane. So the law is applicable in the case of sound also. The next second figure is representing an activity to prove this laws of reflection. That means sound also obeys the laws of reflection. You can check it using two paper pipes or PVC pipes. If you are having PVC pipes Otherwise, simply by folding the paper into pipe form, you can do this activity. Just to keep the two pipes nearby a wall, and then at the one end of the first tube you have to keep any source of sound. You can have a small alarm clock, okay, or any vibrating mobile phone, something like that. And the other second tube, through the second tube you try to listen to that small feeble sound. And it is very interesting that the sound of the source will be very clear or more intense when you are keeping the second pipe at an angle of reflection or angle which is equal to the angle of incidence. That means angle between the first pipe and that screen or the obstacle in between should be equal to the angle between the second pipe and the screen in between. Okay, so this activity you can perform. That means if you are having two paper pipes and with any source of sound, you can prove this laws of reflection, right? I is equal to R. Only when I is equal to R you can have maximum clear sound through the second pipe. Okay. Nextly, echo. Okay. So from the figure, can you guess what is an echo? Or you might have experienced, or you might have heard such an echo, right? Yes, it is actually a reflected sound only. A sound getting reflected from any obstacle, that reflected sound reaching us is called echo. Okay, but every time it is not possible to hear such an echo. So there are certain conditions which should be needed or which should be observed to hear a distinct echo. So let us see what are they. For hearing a distinct sound, the time interval between the original sound and reflected sound must be at least 0.1 second. So that is the first condition. The time interval between the original sound and the reflected sound should be at least 0.1 second. Because you might have heard the persistence of hearing. Whenever we are hearing something, that sound will be remaining in our brain for next 0.1 second. That is 1/10th of a second. Okay, so if the reflected sound is reaching us before that time, then we cannot distinct out the original sound and the reflected sound. That's why it is told that the time interval between original sound and reflected sound must be at least 0.1 second. Similarly, the minimum distance of the obstacle from the source of sound must be 17.2 meter. The minimum distance of the obstacle from the source of sound must be 17.2 meter. Because if we follow the same condition, first condition, time interval between the original sound and reflected sound we know 0.1 second, and the speed of sound at normal temperature we know. If you know the speed and time, you can calculate the distance. Okay. Likewise, we are having the minimum distance between the obstacle and the source of sound as 17.2 meter. Nextly, reverberation. Reverberation. It is also a reflection of sound only, but as you can see from the figure, sound is reflecting several times, isn't it? A particular person is speaking and there are so many persons who are listening to him. And you can see the same sound is getting reflected from different points of the room. From the floor, from the ceiling, from the chair, like that. So, this multiple reflection, the sound is getting reflected so many times or several times. So, that reflected sound, I mean the multiple reflection of sound will be making the sound remain in the room for some more time. Even though the person has stopped talking or he has completed his speech, the sound will be remaining in that room for some more time because of the multiple reflection. Okay, the persistence of sound because of the multiple reflection is called reverberation. Persistence of sound after a sound is produced. That means it is due to the multiple reflection. That is called reverberation. Okay. That means the original sound is reflected several times. So, when the multiple reflections are reaching our ears, we will not be able to hear the or have the clear or we will not be able to listen to the actual speech. Okay, because everything will be getting interfered. And to avoid such confusion in an auditorium or a big hall, the reverberation should be avoided. It is highly undesirable in such an auditorium or big hall. So, to reduce such reverberation, the roof and walls of the auditorium or such halls are covered with sound absorbent materials like plastic or fiber, something like that. They will use such materials for making roofs and walls. Also, the chairs or the furniture in the room will be made of such sound absorbent materials to reduce the multiple reflection or the reverberation. Okay. Now, but in some cases this multiple reflection is desirable. Okay, we are making use of this multiple reflection of sound in several cases. That means certain musical instruments like megaphones, horns, similarly trumpets. Okay, all these are designed to send sound in a particular direction without spreading it in all directions, right? That means megaphones, horns, and also the trumpets, which are the musical instruments, they all are designed such a way that making use of this multiple reflection, sound is made to move in a particular direction only without spreading it in all directions. Next one, as you can see, it is a stethoscope, right? And you know, stethoscope is the device which is used to listen to the sounds produced in the heart or lungs of the human body. Okay, so here also in stethoscope also the sound of the patient's heartbeat reaches the doctor's ears by multiple reflection of sound. As you can see from the figure, the sound is getting reflected several times. Okay, and finally reaching the ears of the doctor. Then another use of this multiple reflection is that generally the ceilings of concert halls, or the big auditorium or conference halls, they will be curved. They will have curved ceilings to make the sound reach all corners of the hall after reflection. Okay, the curved ceilings. Next one, sometimes we may be using a curved sound board behind the stage so that sound after reflecting from the soundboard spreads evenly across the entire wall or entire room. Okay, so soundboard, curved soundboard help to spread the sound evenly across the hall or the room. As you can see from the figure, the curved ceiling of the conference hall make the sound reach all corners of the hall. Similarly, the curved soundboard spreads the sound evenly across the room or the hall. Now, let us discuss certain properties of sound. Sound properties, that is pitch, loudness and quality. They are determined by the wave properties. We know sound is a wave. So, the properties of the wave gives the pitch, loudness and quality. Certain other properties for the sound. Pitch, loudness and quality. You might have heard high pitch sound or loud sound, something like that. Okay. So, what is meant by this high pitch sound or low pitch sound, or what is loud sound, right? Let us see. So, the loudness or softness of a sound is basically determined by its amplitude. Already we defined what is the amplitude of the sound wave. So, amplitude of the wave decides the loudness or softness. You might have noticed some persons, when they are talking, they will be very soft sound, right? But some others will be shouting like anything. Okay, so if the amplitude of the sound produced by the vocal cord of the person is more, then automatically he or she will be able to produce a loud sound, right? If the amplitude is very small, then it will be a soft sound. So the amplitude decides the loudness or the softness of the sound. That means amplitude means that amplitude depends upon the force with which the object is made to vibrate. When you are trying to make sound by hitting on any object, that means you are hitting on your table or your book, something like that. If you are making a large force to hit, okay, then you can hear a loud sound. Okay, so I hope it is clear. Loudness and softness, that depends upon the amplitude of the sound. As you can see from the figure, the sound with the high amplitude is the loud sound, and sound with the low amplitude is named as soft sound. So this is actually the physiological response of the ear to the intensity of sound. Loudness is the physiological response of the ear to the intensity. Intensity actually means energy. How much energy is reaching our ear. So loudness is actually a measure of that energy. But intensity and loudness are not the same. The amount of sound energy passing each second through unit area is called the intensity of sound. Intensity is defined as the amount of sound energy passing each second through unit area. Okay. Nextly, pitch of the sound. You can see in the figure, one is named as lower pitch, other is higher pitch. From the figure, can you identify what factor decides the pitch of the sound? In the first figure, which is named as lower pitch, you can see there are less number of waves, isn't it? But in the second one, there are more number of waves. So the number of waves decides, or number of oscillations or number of repetitions decides the pitch of the sound. That means the frequency. Okay, and if the frequency of vibration is higher, the sound is called a high pitch sound, or it is a sound with the more shrillness. Okay, more shrill sound you can produce if you are able to produce a high pitch sound. If the sound is having a low pitch, then it will be having a low frequency of vibration. Example is that, as you know, a bird can produce high pitch sound, whereas roaring lion, that means roaring of a lion, is a low pitched sound, right? I hope it is clear. The term pitch of the sound, shrillness of the sound, that depends upon the frequency of the sound wave. Next property is the quality or timbre of the sound. So this particular property helps us to distinguish the source of sound from other source having the same pitch and loudness. Understood? That means you people will be able to identify the sounds of your friend or your mother, father, relatives, etc. Even without seeing them, we are able to identify the person, right? Or we are able to identify which musical instrument is being played, even without seeing, just by listening to the sound. Okay, so this property which helps us to distinguish one sound from the other having the same pitch and loudness, that property is called quality or timbre of the sound. And this property depends on the waveform produced by the vibration of the object. What is it? Waveform produced by the vibration of the object. As you can see, the tuning fork is producing one kind of waveform, and the hammer is producing another kind of waveform, and this type of waveform decides the quality or timbre of the sound. Now, range of hearing. We all know that human beings, we are not able to listen to all frequencies of sound waves. Okay, the audible range of hearing for average human being is in the frequency range of 20 Hz to 20 kHz. What is it? 20 Hz to 20 kHz or 20,000 Hz. That is the human audible range. and the frequencies which are lower than 20 Hz are named as infrasound or infrasonic waves, and the frequencies which are higher than 20 kHz, they are named as ultrasound or ultrasonic waves. And some animals like elephants, mole, etc., they are able to produce infrasound or listen to infrasound. Okay. Similarly, cats, dogs, they are also having the range somewhat longer than human beings range, audible range. At the same time, bats, dolphin, they are able to produce sounds in the range of ultrasound also. Okay. So it is have a comparison of ultrasound and infrasound. As we know, the waves having frequency less than 20 Hz are infrasonic waves. A vibrating simple pendulum produces infrasonic sounds. Elephants and whales can produce infrasonic waves. Earthquakes, yes, another point, earthquakes also producing infrasonic waves. The waves having frequency more than 20,000 Hz are called ultrasonic waves. Bats and rats are able to produce such ultrasonic sounds. Now this ultrasound is having lot many applications. That means we can use this particular high frequency sound. Okay, high frequency means it is having high energy also. So using this energy of such ultrasonic waves, we can have several applications in industrial field as well as in medical field. Let us see one by one. So industrial applications include cleaning the parts located in hard to reach places. That means there will be some odd shaped parts or spiral tube, electronic components, etc., which are very difficult to clean. Okay, hard to reach parts. So such parts we can clean using ultrasonic waves. The items or the parts which are to be cleaned, that we will be putting in the cleaning solution, and ultrasonic waves will be passed through that cleaning solution. And you know, ultrasonic waves having high frequency. So when the waves travel to the cleaning solution, the solution also starts vibrating more vigorously, and when the solution vibrates, the dirts and the other solid particles in that parts or the things will be cleaned up. Okay. Next one, to detect the cracks and flaws in metal blocks. In construction area and all, we are using huge metallic blocks and all. Okay, so if there is any crack or any fault in that particular metallic block, we may not be able to identify that. Okay, from the outer look it is okay. Okay, there may be some problem with the inside region or inner region. So if we are having such an ultrasound technique to detect that cracks and flaws, that means you can see from the figure, ultrasound waves are being passed through such particular heavy metallic block, and if there is any crack, the ultrasound is not able to pass through such portion, and the receiving end will not detect any ultrasound. Hence we can conclude that it is having some problem or fault and that particular portion. Okay. Next one, let us have a look at the medical applications. First one, echocardiography. That means to reflect the ultrasonic waves are made to reflect from various parts of the heart and form the image of the heart. Okay, the image of the heart, the doctor can have a view with the help of this ultrasonic waves, because they are made to reflect from various parts of the heart. That is called echocardiography. Next one is ultrasonography. Here ultrasound scanner is being used for getting the images of internal organs of human body. Internal organs of human body like kidney, liver, spleen, etc. Also stomach, uterus, all such internal organs can be scanned using ultrasound scanner. Okay, and also another important application is that the development of fetus in mother's womb can also be scanned using this particular technique, ultrasonography. And next one is for the treatment of kidney stones, ultrasound can be used. That means the ultrasound will be high, as I told, it is having high energy. So high energy waves passing or coming in contact with such kidney stones, the stones are getting powdered up, and this powdered stones will be excreted through the urine. Likewise, for treatment of kidney stones also ultrasound is being used. So this is the one such scanned image of the fetus in mother's womb. Let us continue with another important application of ultrasound. It is sonar. Sonar stands for sound navigation and ranging. It's a device which uses these ultrasonic waves to measure distance, direction, and speed of underwater objects. This technique is used to find the depth of the sea and to locate underwater hills, valleys, submarine, icebergs, sunken ship, etc. And this method is called echo ranging. Now let us see how a sonar is helping us to find the depth of a sea. The sonar having a transmitter and receiver will be situated in the ship. The transmitter is transmitting the ultrasonic waves to the sea. These waves touching the seabed gets reflected back, and the reflected ultrasonic waves are received by the receiver. So by knowing the speed of sound in water and by noting down the time taken by the ultrasonic waves to reach the sea and back to the ship, we can calculate the distance. So if the time taken for transmission and reception of ultrasound is t and the distance travelled is 2d, 2d comes here because the sound wave is travelling from the ship to the seabed and back to the ship. Hence the distance travel, total distance travelled by the sound wave will be 2d. So 2d we can have, it's equal to v into t because distance is equal to speed into time. So here the speed will be speed of sound in water. Time already the time what we are noting down. So 2d is equal to v into t, and therefore d is equal to v into t. So the echo ranging technique by sonar. Okay, sound navigation and ranging, that also employs ultrasonic waves. Okay, now we've seen that several other animals also are able to produce ultrasound. So this high frequency or high energy ultrasounds help certain animals also in several ways. As we know, bats, rats, dolphins, etc., they are able to produce ultrasound. And bats produce these ultrasonic squeaks, and these reflected ultrasonic waves which are touching on the prey. That means the ultrasonic waves touching on the prey or any obstacle get reflected back, and these reflections, nature of these reflections helps the particular bat to predict where the obstacle or the prey is and what it is like. Okay, so the bats produce ultrasound, and this ultrasound helps them to detect the presence of any prey on their path. Now we are going to discuss about the structure of our ear. As we can see, the human ear is having the first part called pinna. Pinna is also called the outer ear. The sound is collected by the outer ear. That means that from the surroundings, the outer ear or pinna collects the sound. And this collected sound is travelling through the canal, ear canal called auditory canal. At the end of the auditory canal, there is a thin membrane called tympanic membrane or eardrum. And we know that the sound is a set of vibrations, that means compressions and rarefactions. As per these compressions and rarefactions, the eardrum also starts vibrating. That means when the compression comes, the eardrum will be moving forward or pushed forward. When the rarefaction comes, it will be pushed backward, like that. So these vibrations are reaching the eardrum. Now from the eardrum, the sound vibrations reaches the middle ear, which contain three bones: malleus, incus and stapes. They are also named as hammer, anvil and stirrup. You know, the smallest bone in our human body is situated in our ear, which is stapes or stirrup. So the role of these three bones is to amplify these sound vibrations. So sound vibrations reaching the middle ear are getting amplified by the three bones inside the middle ear, and this amplified vibrations reaches the inner ear. Inner ear contains another structure called cochlea, which convert these amplified vibrations into electrical signals. These electrical signals then reaches the brain via the auditory nerve. Right? So hence we are able to interpret the particular sound, or this electrical signals reaching the brain help us to hear that sound. So the human ear contains outer ear collecting the sound vibrations, middle ear converting the sound vibrations, or amplifying the sound vibrations, and inner ear converting this amplified sound vibrations into electrical signals. Okay, these electrical signals reaching the brain via the auditory nerve help us to hear. Okay, so I hope all of you understood how we are able to hear sound. All these things are happening right now inside your ear, isn't it? Very much excited, right?
So I hope all of you enjoyed the lesson, isn't it? We discussed the method of production of sound, propagation of sound, different properties of sound, then reflection of sound, etc. etc. Right? Then ultrasound, infrasound, the applications of ultrasound. One main point is that sound is traveling as a wave, and it is one type of wave called longitudinal wave, because we see that the sound contains a set of compressions and rarefactions, right? So this compressions, rarefactions means particles are vibrating parallel to the direction of motion of the wave, and hence only the sound is named as longitudinal wave. So we discussed the several applications of ultrasound, then sonar, sound navigation and ranging, and also we discussed the structure and functioning of our ear, isn't it? So I hope all of you understood the topics, and you have to read the lesson thoroughly, and all the best, dear children.